Welcome back in our course. So, we were discussing about the dynamics of the moving system, and in particular we were talking about the eddy current damping. Okay. So, let us recall it briefly. So, we were considering the PMMC instrument. So, we have these two poles, north and south. Between these two we have a moving or a rotating coil like this, and then this coil must have a closed circuit through the external circuit when it is measuring something. So, let me draw some circuit to which this coil is connected. Because we are measuring something, that means the coil is definitely connected to some circuit in which current flows, and this circuit can be very complicated in general, but let me take a simple circuit like this. Okay. Now, we have seen that the flux lines are like this, and in this circuit now there should be no current, because according to my diagram there is no source, there is no voltage or current source which will drive any current. Okay. So, this is a very simple circuit, but even now if the coil starts to move by due to any reason, if it starts to rotate, then this is a coil inside a magnetic field. So, it is like a motor, it is basically like a motor where we have a coil inside a magnetic field. So, some EMF will be induced because the sides of the coil are moving through the magnetic field. So, some EMF will be induced, and this EMF will cause some current to flow, and then using Fleming's Fleming's right hand rule, we can find out the direction of the EMF, thereby the direction of the current, and then using Fleming's left hand rule, that is motoring rule, we can find out the direction of the force or torque which will act on this coil. And in our previous video we have seen that this force due to the induced current is always in the direction opposite to the motion or the velocity or angular velocity of the coil. So, this force always tries to stop the velocity of the coil, and this current we can call it eddy current, and therefore, we can call this damping mechanism as eddy current damping. And in our last class we have seen that the damping torque, so T damping, okay, this is the damping torque. We have seen this is the magnitude of it is proportional to the velocity, this is the angular velocity d theta dt, and multiplied by g square by the total resistance in the circuit, which is coil resistance plus external resistance, and where G is BAN, flux density, area of the coil, and the number of turns. Okay. So, this is this force, and also this force acts always in the direction opposite to the velocity or the angular velocity of the coil. So, I can actually erase this mod sign and put a negative sign here to indicate that the direction of the torque is always opposite to the direction of the angular velocity. Okay. Yeah. Now, the problem here is this torque T damp depends on RE, that is the external circuit. And so, if we are measuring current in different circuits, RE will be different, and therefore, this damping torque will also be different. RC is constant, coil resistance is constant, but external resistance is not in our hand. I mean, it depends on the external circuit. So, T damping or damping torque depends on external circuit, and therefore, this is not very controllable. I mean, we cannot control the amount of damping torque or damping force at our desire. So, we will consider now a small variation of this scheme, which is the eddy current damping due to the eddy current in the former or frame of the coil. Okay. So, recall that this coil is wound on top of a former or frame, a rectangular frame, and that looks like this. And this is made up of aluminum, which is a conductor, okay. So, this is a frame and the coil is wound on top of it. So, the coil goes like this, and so on. Okay. Now, this former itself is a conductor. This is made up of aluminum. So, this is made up of aluminum. So, this is conductor. Now, therefore, this frame can also be thought of as a single turn coil. Okay. So, the frame acts like a single turn coil. Okay. So, we have the frame here inside the coil. So, this is the frame, and this itself is a closed circuit. Okay. So, this acts like a one turn or single turn coil. Okay. So, therefore, if this coil is rotating, that means this former frame is also rotating, because the coil is attached to the frame. So, if this coil or the moving system is rotating, then in the single turn coil, that means the former will have some EMF induced. Okay. And that EMF will cause some current to flow through this coil. That means, actually this former, this single turn coil. Okay. So, so when the coil moves, the former also moves. Former means frame. So, EMF is induced in former. So, some eddy current will flow in former, okay, and therefore, this eddy current will now generate a torque which will oppose the velocity or the angular velocity. Okay. And thus a torque is developed which opposes the angular velocity. Okay. Now, just for our practice, let us derive the expression for eddy current, the torque due to eddy current in the former very quickly. The derivation will be very similar to the derivation of the damping torque due to eddy current or due to the induced current in the coil, but we will do it once again very quickly for our practice. Okay. So, let us do it. Assume the flux density to be B, assume the length of this former to be L. So, this is the length of the former, then the diameter or the width of this former, call it W or call it D as per the standard notation. Okay. So, now the consider any one side, consider one side, this side, how much flux is it intersecting per unit time? Okay. For that we need to know the linear velocity of this side. So, angular velocity is d theta dt, linear velocity will be angular velocity multiplied by the radius, that means d by 2. Okay. So, this is the linear velocity. So, the rate of so the induced EMF which is same as the rate of flux intersection So, this will be same as this velocity multiplied by the length. So, this is the area swept per unit time by this conductor side multiplied by the flux density, flux per unit area. So, this is the EMF in one conductor or in one side. Okay. So, total EMF will be 2 times of this. So, 2 multiplied by d by 2 d theta dt L b. Now, this 2 cancels, dl is equal to A, area of the coil or the inside of the former. So, this we can write as A B A times d theta dt. Okay. The difference in this expression from the expression of the EMF in the coil was that we do not have the term N here, because N, the number of turns for the former, is equal to 1. Okay. So, maybe we can write that N is equal to 1 for the former. So, now what will be the current? Current will be EMF divided by the resistance. Resistance of what? This will be the resistance of the former. You see, this former is a closed loop, it is a closed circuit. So, this closed loop will have some resistance. Okay. So, that resistance we have to put here. So, resistance of the former. Okay. So, this will be the current. So, and then the torque will be how much? B A n is equal to 1 in this case, you can write it like this, n is 1. So, B A n times the current, which is equal to B A times EMF. Now, in place of EMF we can put this expression B A d theta dt and divided by former resistance. Okay. So, this becomes B A square d theta dt by R former. N is equal to 1, the number of turn of the former is equal to 1. So, that was a very quick recapitulation of the derivation, how to find the torque eddy due to the eddy current damping. And once again you see that this torque, okay, so let us write it, this torque T damping is, you see, it is proportional to d theta dt as we always want, multiplied by B A square by R former, and we can put a minus sign here to indicate that this direction of this torque will be in the direction opposite to d theta dt. So, here we considered only the magnitude of the torque, okay. We did not consider this sign in this line of the derivation, but now using the Fleming's rules, left hand right hand rules, we can find the direction and we can show once again that this direction will be opposite to the direction of the velocity. And I request all of you to kindly do this small exercise, apply Fleming's right hand rule first to find the direction of EMF and then apply Fleming's left hand rule to find the direction of the torque. Do this exercise, it will be a fun. Okay. So, that is the damping torque. Okay. So, what have we seen so far? So, we have seen that there are a number of forces or torques acting on the moving system that means the coil plus the former frame plus the pointer and everything else which is attached to this coil, etc. Okay. So, the torques that act on this moving system are firstly the deflecting torque, which we denote as Td, then the controlling torque, this is nothing but the spring torque, which we denote by Tc, and the third important thing which we have discovered now is the damping torque. So, let us denote it as T damp, because if I use Td, these two will be confusing. Okay. Now, what does this torques depend on? This, say, controlling torque, this depends only on the position of the coil. So, this depends on theta. Okay. So, that is the angular position of the moving system. This torque Td, it primarily depends on the unknown current or maybe voltage that we want to measure, unknown current or voltage. that we want to measure. Okay. And this torque depends on the velocity. Okay. Therefore, T damping is equal to 0 at steady state or equilibrium. If the pointer stops at any position, if the coil stops at any position, then d theta dt will be equal to 0. Okay. So, because this velocity is equal to 0 at equilibrium. That means, when the pointer has stopped, and then only these two forces, these two torques are active, and they should be equal and opposite in magnitude. Okay. Now, in this video, the last thing that we will do is the equation or the dynamics or you can say equation of dynamics or equation of the moving system. Okay. Suppose the we denote by the symbol J the moment of inertia of the moving system. That means, coil plus pointer plus the frame, everything together which moves together. Okay. So, this J, moment of inertia, so this is something like the mass inertia for angular motion. Okay. So, this is the moment of inertia of the moving system. So, therefore, we can write that J, that means the inertia multiplied by the angular acceleration okay. So, this is moment of inertia, this is angular acceleration. Okay. Now, this should be according to Newton's law for angular motion should be equal to the total torque acting on the system. At any moment, always. Okay. So, this is Newton's law, Newton's second law, inertia times the angular acceleration should be the total torque. Now, the total torque should be, so this is a sum of these three torques, deflecting torque, controlling torque and damping torque. So, therefore, we can write that this should be equal to T d, okay, which is primarily a function of the say unknown current when you are measuring say a current in a PMMC instrument, for example. So, T d, this is primarily a function of the unknown current, particularly for PMMC instruments we know this is equal to BANI. So, therefore, it is only a function of the unknown current. Okay. So, we are considering PMMC as an example now. So, this is the deflecting torque, okay, and then we will have the controlling torque. So, the controlling torque is Tc, which is mainly a function of the angular position theta, and then we will have T damping, which is mainly a function of the velocity. We can write it further as Td I plus Tc theta. We know this is according to Hooke's law is equal to k theta. Okay. But now we will put a minus sign to indicate that this force is always in the direction opposite to theta. That is what Hooke's law says, that the spring should always try to should always give a force in the direction opposite to the theta or the twisting of the spring. So we have a minus sign. Now in place of T damping we can write, so we know that T damping should be, or we want it to be, proportional to d theta dt with some constant, call it k damping. So this is damping constant, and we put a minus sign. Why? Once again we know that this torque is always in a direction opposite to the velocity. Okay. So this is the equation for the moving system. Now we can rewrite it by slight reorganization of the terms. So we bring all the theta dependent terms on one side. So this is the second derivative of theta. Then let me write the first derivative term, which will be k damping multiplied by d theta dt. The minus sign will become plus when I bring it to the left side, plus this k theta. So this is spring constant. Okay. So this, let me write, is damping constant and this is spring constant. Okay. And then, so this should be equal to the deflecting torque T d function of, maybe a function of the current or unknown voltage that we want to measure. Okay. So this is spring constant. Okay. So my computer is getting slower, indicating that it's time for me to stop this video, and therefore we will continue on with this topic in our next video. Thank you.